So we start. So we're still looking at the fixed point iteration method, and this is the third question from the tutorial sheet that you guys shared some days ago. Okay, so I have one question here. So the question reads, use the function g of x equal to 20 minus x in brackets to the power 1 over 3 to solve the equation x cubed plus x equal to 20 using the fixed point iteration method in the interval from 2 to 3 with the x naught equal to 2.4. So x naught is simply the initial condition. So every time, in fact, you are using fixed point iteration method, you need to have the initial condition, okay? So the initial condition has to be given to you, or you have to just guess, just like the situation that we had yesterday. I'm sure you saw where we're trying to approach a given value. Okay, we are trying to confirm that okay, we are converging to this value. So we just guessed, okay, just picking one value which is close to that value we're trying to converge to. Okay, so with x not equal to 2.4 to a 5% error. So what is this 5% error telling us? This 5% error is simply the stopping criteria for us. It's telling us when are we supposed to stop? Okay, remember it's a iteration method, so can go up to infinity, you can do as many iterations as possible. But this time around, we are told that, oh, you have to stop when the error is 5%. And which error is this? This is what? The relative error, actually. Okay, we are using a relative error to stop our criteria here. So with me here, I've listed the important parameters. So we are given the initial condition, which is x naught, which is 2.4. We are given error, which is percentage error, 0.005. Okay, so I put in decimal. And then the function is given to us. In fact, this function,
Steven,
yes, please.
isn't it supposed to be 0.05?
Oh, sorry. Yeah, so yeah, you're right. That's 0.05. I just had to add some zero. I just did it in my head, of course. Thank you for that. Okay, so this is 0.05, yeah? So we stop when the error is greater or equal to 0.05. Okay, so this equation here, the one we are trying to use, the function we're trying to use, which is g of x equal 20 minus x to the power over 3, actually comes from this equation, right? So you can see that if you solve for x cubed, okay, you take x to the other side of the equation, okay, so you're going to have 20 minus x, and then take the cube root of that, you end up what? Having this. So this was the original equation, but remember what you said last time that, oh, when you're using fixed point iteration method, you have to arrange the equation in this form, right? G of x or something, okay? All right. So we may start. So we are given the initial conditions. Okay, the initial condition given to us is x naught equal to 2.5, right? Okay, this is where we're starting from. Okay, so every time we're doing the iteration, okay, we have to check this condition, the relative error. So relative error is simply the difference between the present approximation minus the previous approximation divided by the present approximation. Okay, so xn is simply the present root, while xn minus 1, I'm taking this as what the previous root. Okay, so we'll be checking every time. Once we get the root, we check this condition and then we compare with it 0.05. Okay. So what I'm trying to say here, we are given the initial condition which is 2.5. We are given the function g of x, which is 20 minus x to the power 1 over 3. I said this function actually comes from this cubic function, which is x cubed plus x equal 20, right? So every time we do the iteration, this equation is the one that we use when doing the iteration, remember? Okay, and the next value, which is the next root, you have to plug in the previous value in the function, right? So we'll be checking this is actually the equation that we use. Okay, remember that. Okay. Now, remember we are given the stopping criteria, right? We are given when we are supposed to stop, right? Okay. So we are told when we are supposed to stop. I'm supposed to stop when the error is simply 5%, which is the relative error. So we have to use this condition here. Okay, relative error is denoted by epsilon. Okay, so then I'm using epsilon as notation. Is equal to the difference between what the present value. Okay, the present value is the value that we are just from calculating when you use the equation, right? Okay, minus the previous value, the value that you previously calculated, divided by the present value. So every time you have to be checking, you do the iteration, you have to be checking that this guy here must be less or equal to 0.005. So it must be greater. You only stop when this guy is greater than or equal to 0.005. Okay. Otherwise, if it's less, then you have to continue doing the iteration until this condition is met. So this just it tells us when we are supposed to stop. Are we together?
Yes, we are. Thank you.
Okay. Okay. So now let's start. So with this initial condition given here, the equation already is written in standard form to us. Okay. So they've already written the equation in standard form to us. But in the situation where the equation is not written in standard form, please write it in standard form when using fixed point iteration method. And you know that I said, okay, there are so many forms, different forms you can write the equation, but you have to check that, okay, that equation, remember those conditions looked at last time? Okay, if there's a fixed point method in the, if there's a fixed point in the given root, those conditions have to hold. So in fact, we can even check, since we're given the interval already here, okay, just to refresh your mind about the conditions that we looked at fixed point, we can actually check. So let's check if this is true, okay? So before we start solving, I'm going to check those conditions that we discussed last time. Okay, so the first point is that it must be continuous, right? The function is g of x. Okay, I'm just trying to revise this condition, right? Must be continuous. So continuous on that interval, right? On that interval, which is what? 2 to 3. And you can see that that function is actually continuous because if you put any value of x in the function, it will still hold any value from 2 to 3, it will still hold. So it's actually a continuous function. And then next, we have to check that, oh, g of x must belong to the interval, right? So g of x must belong to the interval, right? What I mean here is that, okay, if you substitute any value from this interval here, okay, if you substitute any value from this interval here, you must get the value which is within the interval. So how you can test it is actually by substituting the extreme values of this interval, meaning 2 and 3 actually. Okay, that's the easiest way to tell, of course. Though there might be some values that may not hold in between, but in most cases, okay, depending on the nature of the function itself, of course, okay, it may not be true all the times. But yeah, this is most cases, that's what holds, right? Because the interval is so small, so don't expect that, okay, in this interval, maybe the function has maximum at some point in between. So let's first g of 2. Let's check, okay? So for x equal to, let's check if what you're going to get will be within the interval. Okay, so we're going to substitute g of 2 is equal to 20 minus 2 to the power 1 over 3. Okay, so what is 20 minus 2? That is 18. So 18 to the power 1 over 3. So this is 2.62 something, right? So you see that this guy is actually in the interval, isn't it? Okay, because 2.62 is actually in that interval. You can also check for 3, right? You can also test 3. So 3 is equal to, if you substitute 3 here, you're going to have 20 minus 3 to the power 1 over 3. So this is 17 to the power 1 over 3. What is 17 to the power 1 over 3? Look.
2.5712.
2.57, okay, whatever. So even this value is actually in that interval, right? Okay, the last condition, we need to check the derivative, right? The derivative must be less than 1, isn't it? Okay, we discussed that last time, right? So we have to check the derivative also. Okay, so the next condition, we have to check that, okay, g prime of x on that interval, of course, we're just tracing the absolute value, must less equal to k, where k is less than 1, right? So if we take the derivative of the function and then substitute any value of x in that interval, that value you get must be less than 1. Okay, so let's check also. So we know that our g of x is equal to 20 minus x to the power 1 over 3. Now let's take the derivative of this, okay? So g prime of x is equal to, we remember the derivative, we drop the powers, so we have 1 over 3, 20 minus x, and then power, we subtract the powers, isn't it? So subtract power, what is 1 over 3 minus 1? So this is what? Negative 2 over 3, isn't it? Right? Is that correct? Okay, so negative 2 over 3.
Yes.
Okay, and then remember we're using chain rule, we can't just let it like this, right? So also we differentiate what we have inside, isn't it? Chain rule, don't forget. So what is the derivative of 20 minus x? That is negative 1, right? Because 20 is just a constant. The derivative of negative x simply negative 1, isn't it? So negative 1 here, and then overall you're going to have negative 1 over 3. Okay.
You've written negative 2 over 2.
Oh, okay, sorry. Negative 2 over 3, thank you. Okay, so you have negative 1 over 3, and then 20 minus x to the power negative 2 over 3. Okay, all right, so at this point, you know that if we have a negative power here, we can actually drop this guy in the denominator also. Is it? It's allowed, isn't it? Okay, it's very much allowed, right? So you can do that, we drop that, so we're going to have a negative, in fact, on top, we're just going to have a negative 1. Everything, even 3 is in the denominator, okay? And then in 20 minus x. So if you drop this guy in the denominator, you see that you have 2 over 3 comes positive, right? So this is the derivative g prime of x, right? Okay, and then now we have to check now. So, oh, okay, if we substitute any value of x now from that interval, what do we get? Are we getting something less than 1? Okay, so we are just tracing the absolute, right? So not tracing the sign itself. So the sign is not even necessary at this point. So just the absolute value of that. So let's see the absolute value of g prime of x. And you can say you don't have to check. Already this value is divided by 1 over 3. And this one also, if you substitute any value here, it will also be greater than 1. So clearly this guy is this and 1, isn't it? This fraction, right? Is there any dispute there? We can all see, isn't it? Hello?
Yes.
Why are the other people? Why are you people quiet? Why are the other people? Clearly this guy is this and 1, whether there is a fixed point in the given interval. Which arrangement are we supposed to pick? So every time when it's open, you're just given, I'm just saying this in case the question just comes, like you're just given a function which is not arranged for you, okay? You have to arrange it. So you solve for whatever arrangement you're going to, if you wanted, you could have solved for x, take x to the other side and then check this if it's true, okay? Do whatever you want to do. Make sure that, okay, you check the conditions and then you'll be able to say, okay, this one converges actually, okay?
I have a question.
Yes, please.
What if condition number 2 doesn't qualify, or maybe any of the conditions, but
Then
the other two qualify? What do we do?
Okay, the first two, if the first two qualify, okay, if the first two qualify, there is a fixed point, okay? So these two talk about a fixed point. There is a fixed point. And then this one here, if the third one qualifies, then there is a unique fixed point. It's a combination now. Okay, so meaning the fixed point that you have is actually unique. So yes, there may be a fixed point, but not unique. It means that uniqueness means you just have one, right? One maybe, so that's one fixed point that you get in that interval, right? That's the uniqueness we're talking about. Okay, but these two are the first two are a must in both cases. Okay, these can't work without the other one. These two must be continuous, and the g of x must be a member of that interval. Okay, this, yes, even if this one fails, if this one fails, tells you, okay, the fixed point that you have is not unique on that interval. Okay, if this one fails, the fixed point is not unique, but there is a fixed point, but it's not unique. Maybe you have about 2 or 3 of them fixed points.
So when checking, sorry,
yes.
so when checking, if they haven't given us the equation to use, so we need to make sure that 1 and 2 has to be satisfied.
Yes,
for
1
us
and
to
2
use.
has to be satisfied. Yes. 1 and 2, it's a must. The function itself must be continuous on that interval. That's compulsory, it's mandatory. And also g of x must belong to that interval. Okay, that is a must. Is that clear?
Yes.
Yes. So if those two conditions
I
are
also have a
met,
question on the first condition.
yes, please have asked.
So how do you determine that it's continuous? Do you substitute the variables in the equation, or I'm not so clear on the first one.
Okay. The continuity of a function. Okay, let me just sketch this for you. Okay, let's say you have a function like this, right? I'm going to sketch two graphs. Okay. Let's have this function here from this interval 1 to 2, right? Okay. Okay, let's say this function looks like this, right? So the first function looks like this from 1 to 2. Okay, so from this interval from 1 to 2, this is it. I'll say f of x. I'm going to sketch another function. Another function looks like this. Okay, so from the same interval 1 to 2, but this guy, okay, so at this point, it's piecewise. What does it mean here is that at this point here, that function is not continuous. As you can see, there's a hole, okay? Or sometimes you find that there is an asymptote, right? Let's say that some functions that have asymptotes. For example, I'll give you several, I can give you an example where the function is not continuous at that point, especially functions that are fractions, okay? If you have a fraction, if you have a function which is a fraction, yeah, we have x in the denominator, check very well. For example, if 1 over x, you see that this function is continuous everywhere for all values of x, except what? X is equal to 0. So this is the reason 1 over x function never touches the x-axis, I mean the y-axis, and never touches the x-axis, of course. So you notice that this guy has vertical asymptote for what? Along the y-axis, because you never touch the x, you never touch the y-axis, and also this side it appears like this. Okay, it also appears like this. So this is how 1 over x is. So it means that if for x is equal to 0, this vertical asymptote, this y-axis, this function is not defined because you're going to have 1 over 0 the denominator. So for on time, when you have a function not continuous, you have to check the denominator. So all the functions that are in this form, if there is no fraction involved in it, for example, this guy accepts all the values of x, in fact. Okay, all the values of x. So for rational function, you have to check, right? So for example, like square root function. For square root functions, okay, for square root function, instead of a function like x plus 2 in square root, right? Okay, you know that square root cannot accept negative values. You know that fact, isn't it? Hello?
Yes.
Okay, so if you have
Yes.
a function f of x, you know that square root cannot accept it. Accept what? 0. So the only way this function, this guy can only accept positive values starting from 0 up to infinite. So you're going to solve, okay, what values of x must I get? Okay, what values of x must I get for this to be defined? So it means that if you solve, equate this guy equal to 0, you notice that the values of x are supposed to start accepting should start from what? -2. So meaning x should be greater or equal to -2. Those are the values that we're going to accept here. At the point when x is just greater than negative, when x is less than -2, let's say we have -2.1, this thing becomes invalid because we're going to have a negative now in the square root. So it's continuous for all the values that are greater, that are less than -2, meaning starting from -2, going to infinity this way. All these values, the function is not continuous. That's the meaning of a continuous, the function being continuous. So in that interval, are you getting something like having a negative in the square root, or are you getting something having a 0 in the denominator? When you substitute any value in that interval, and what value should it be? Okay, so if you are given like a fraction, I'm going to explain something again. If you are given a fraction like let's have x squared, let's say you have 2x, right? Let's say you have 2x plus 3 on top. Okay, this x squared plus 3x plus 2, for example. Okay, this is a function g of x. Okay, so what values of x are they going to make this function not continuous. So the Zonda asymptote, that's not the case. Okay. So we are mainly focusing on the values of x that are going to make this function 0. Okay, in the denominator there. Because every time we're trying to avoid having a 0 in the denominator. Okay. So if you notice here, if you had to factorize that function in the denominator there, you're going to have what? X plus 1 times x plus 2, isn't it? Right? So you notice that this, the values of x are supposed to get here. It is discontinuous at what point? X equal -1 and x also can never be equal to -2. Because if you put -1 in here, you're going to have this as 0. And we have a situation where we have a number over 0. And also x can never be equal to -2. So you notice that whatever form of this function is, I don't know it very well though, whatever form it is, at -1 and -2, this function is going to have asymptotes. Okay, it's going to have asymptote. It never approach that. Okay, it will be more like approaching it but never touch it. That's an asymptote. So to mean that at that point is discontinuous. Okay, it's not defined at that point. So that's the meaning of a function being continuous. So you check the interval here. What value of x can I put is going to make this function disqualified? Am I making myself clear on that one?
Yes, sir, you've really explained it well. Thank you very much.
Okay, okay. So from the problem that is given to us, see, you notice that we have 30 minus x, the power 1 over 3. You know that cube root, you can find the cube root of a number either positive or negative. Okay, isn't it? So
Yes.
this one is continuous everywhere for all the values of x can put here. Even if we outside that interval, this function is to be valid, is to be continuous. But if we are the square root, then we are going to have restrictions. Because if we have a square root, then you notice that the only way this function can be continuous is by making sure that this guy in the brackets, it must be greater or equal to 0. Okay, that's the only way. Should be greater or equal to 0. Because remember that when you find the square root, we are only interested in the positive values. Okay, so if you solve for x here, you're going to have negative x greater or equal to, this will be negative 30 divided by negative here. Negative here, remember that every time you do that, the sign has to change, right? This should be less or equal to 30. So it means that the values of x that this is going to accept should be less than or equal to 30, meaning starting from 30 here, going to negative way, it's going to accept. Because every time we put a value which is less than 30, this value will be positive all the times, right? But if you put a value greater than 30, then you have a problem. For example, 31, you're going to have 30 minus 31 over negative. The square of negative, it's imaginary number, it's complex number, isn't it? So it's not continuous for the values greater than or equal to 30. I mean, so for the values that are greater than 30. Okay, for the values, all the values that are greater than 30, the function is continuous. If this one was 1 over 2 as a power. Now, since we have 1 over root 3, it's continuous everywhere. Doesn't matter which value of x you put there, it's always continuous. So that's the meaning of continuity.
All right. Thank you, sir.
Sure, sure. Has everyone understood what it means when say, okay, the function is continuous on this interval? Have you guys understood?
Yes.
Okay.
So
Then let's go. Sorry?
I have a question.
Yes, please, go ahead.
So if we're told to find the uniqueness of the function, how do you find that?
The uniqueness of function is now by checking this derivative property here that I've just explained. The derivative must be less than 1. Then you conclude that, oh, that one actually, it's the function is as a fixed point and the fixed point is unique.
Can you find the actual value?
The actual value of what? Yeah, you can find the actual value. Yes, of course, you can. You can find the actual value.
Okay.
So the actual value is actually by substituting what? Remember that you always write x is equal to g of x. So what it means that the function has a fixed point on that interval. It means that if you put in, let's say, root p in the function, it will give you back p. I'll give you an example of, let's say, in fact, this is a very good example. Pi minus
Can
sine.
we use the same example?
Sine x, right? Okay, oh, wait, we'll see, we can use the same example here, so we'll use it later. Okay, I think, is this sine? Oh, no, let's say it's cosine. Yeah, cosine. There's this example that, okay, cosine x. This guy's unique fixed point, okay, as a fixed point at what? X is equal to 0, isn't it? Because you notice if I plug in 0 in this function, so if I plug in 0 here, so I'm going to say g of 0 is equal to pi minus cosine. Oh, no, not 0. Let me just, if I this should pi should be 1. Let me use 1 here. 1 minus cosine. Okay, so this is it. But then I can still maintain the same pi. What I'm going to do here, I'm just going to put a pi in front. Okay, a pi in front, right? So I'm going to have cosine 0, right? So what is cosine 0? It's 1, right? So I'm going to have 1 times pi. Pi minus pi, you have 0 still. So you see that you plugged in 0, you get back 0. So that's a fixed point. Okay? What you put in the function, it will still give you back the same thing. That's what it means, a fixed point. Okay? So that's the meaning behind fixed point. What you put in the function, it gives you back the same result. Okay? So now, we'll come back to your question. I think let's just first start solving this problem. We can do it afterwards when we found the answer. Okay? Is that okay?
Yes.
Yeah, let's just continue because may waste some time. There are so many questions to look at also. So let's just continue. Okay, now let's start the iterations. Okay, so having checked the conditions, though it wasn't a requirement for us to check, but I just wanted to prove to you that, okay, if you doubt that this arrangement is not okay, then you can check the conditions if those conditions are met. Okay, now let's start. So we are given P naught or X naught. Oh, this is X naught is 2.5. Okay, so we have
It's 2.4.
2.4. Okay,
Yes, it's 2.4.
So we have X is equal to, so we have G of X, of course. So G of X is equal to 20 minus X to the power 1/3. So remember the equation that we use is Xn, the next root is equal to G of X of n minus 1, the previous root. Okay, so that's our X of n minus 1 in this case, we are taking what? X naught as. So in this case, our X of n minus 1, it's X naught. That's where we're starting from. So we're going to start with X1, right? So I'm going to draw a table. I think let me just draw a table. You guys will be giving me the values in the table. So I'm going to draw a table. Okay, let me just draw it here. Okay. So here I'm going to say any value. Okay, I'm going to take this as any value. And then this is xn. So I'm going to start from n equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Like that. Okay, so for n equal to 1, so you're going to have x of 1 equal to g of x0, isn't it? Because plug in n equal to 1, you're going to have a g of x0 here because n 1 minus 1 will equal to 0, right? So you start. So what is the x1? So x1 will be equal to, we substitute the function, okay? 20, our g of x is 20, right? 20 minus what? So x naught, in place of x, put the initial condition 2.5. Oh, it's 2.4, right? Why am I? Oh, so 2.4 to the power over 3. So what are you getting as x1?
I'm getting 2.6011.
Yes. 2.6 what?
2.6011
2.60
011
Uh-huh.
82894.
Okay. And then let's get, so this is x1, so it's 2.60118, whatever there. And then let's get x2. So we're going to use now the previous value. So the previous value is what? 2.60118, whatever there, the power 1 over 3. So, what value are you getting here?
2.59
2.59
12
12
33647.
33647. Okay, great. And then let's get x3. So now, before we do that, let's now start checking the condition, right? Okay, so the condition, we know that we have to check for this. Okay, so write it here. We have to check for this xn minus 1 divided by xn. Of course, you just need the positive value of it, absolute. You have to check that this is greater than or equal to 0.005. So let's start. So we start with the xn. So our xn in this case, so we're going to use x1 and x0. And also we're going to use what? x2 and x1. So we have three values of xn, of course. Okay, we have the starting value, which is 2.4. And then we also have x1. So we're going to check twice, right? Since we have three values. So our xn in this case was 2.60, whatever there you can substitute, minus previous value was 2.4, divided by what? 2.6011. So how much are you getting this? From this, how much are you getting?
Uh, 0.0773134444.
So this is 0.07.
077.
Okay, avoid
Zero.
the waste, not to waste time. Why am I writing 0.005 here? So already let's not waste time, right? This value is greater than what? 0.05, right? So you can stop, isn't it? This value is already greater than 0.05, okay? Okay, now let's check the next one. So what will be the present value now in this case will be x2. X2 now becomes our present value, is 2.591. The previous value is what? 2.6011 divided by 2.591. So again, let's check this one. What are you getting?
It's absolute, yeah. 0.003898.
003.
Yeah, 3898.
So for the converge then, look at how quick it is to converge. Okay, so you see that this value now is less than. Okay, sorry. Actually here, I made a mistake, right? This sign has to be not greater than, but should be less than. Okay, sorry for this. This value should be less than or equal to. Okay, should be less or equal to, not greater. Okay, sorry for that. Okay, because make sure that your error is as small as possible. So you stop when this value, this error is less than or equal to 0.05. Okay. So you notice that this already we have converged, not so.
Yes.
So we've already converged. So our value, which is the root, is equal to 2.5 something, right? 59, whatever. For that value of converged for. So of converged when you are finding x2, 2.51233. 647. Now, you people, look, we've just done how many iterations? Just 2 iterations. We've already converged to the according to that rule which is given. Okay. Now, imagine if you are using a fixed point iteration method. I mean, if you are using bisection method, try to check how many iterations you're supposed to do. Okay, come back and confirm how many iterations you're supposed to do. Just the same problem. So the question you're going to use now this time around, you are going to use this equation, okay? This one, which is not simplified. That's what we're going to use when doing the bisection method. Try to compare the two. So use this equation x2 plus x for 20. And of course, don't need the initial condition. So what you need to use, the initial condition you're going to get is what? By doing what? Adding this plus this divided by 2, isn't it? That's the initial condition you're going to have, right? When using bisection method. Try to check to see how many iterations you're supposed to do for you to reach this 5% error.
I think
You see that
we can
sorry?
use that formula in bisection. If
Uh-huh.
you want to compare, we can use that formula for
Yes, in
finding
fact, yeah, this is now
number.
the time that you can even use that formula. Of course, okay, let me check now how many iterations you're supposed to do. Okay, try to check it. I'm not going to check it here, but you can use this formula. B minus A I'm using black. B minus A over 2 to the power n less or equal to 0.005, right? Or 0.05. Check how many iterations you're supposed to use here for you to achieve this. Okay? That's your homework. All right. Okay, so now someone was asking about how can you find that fixed point, right? Someone was asking about how can we find that fixed point, okay? So the fixed point is found by, remember that we say, oh, P is equal to, should be equal to G of P. When you substitute P in the function, it gives you back P, right? So what we have here is G of X is equal to what? 20 minus X to the power 1 over 3, right? So this will be G of P. You can substitute P, okay? So this is G of P equal to 20 minus P the power 1 over 3 should be equal to what? P. When you put P in the function, give us back P. So this equation is supposed to solve. Solving for P, that's it. That's a fixed point you're looking for. So 20 minus P, the power 1 over 3 equal to P. Okay, so we're able to solve this equation. So it's just as good as solving this equation. In fact, it's as good as solving this equation itself. This one. And do you know the way of solving this equation? How can you solve it? Let's see. Okay, let's see. Just give me a minute. Let me go to the calculator. I see if I can be able to solve it. Okay, to the power 3. Plus 6. Plus what? Is it plus 20, right? Or minus 20? Is it minus or plus? No,
Minus 20.
Minus 20, right? Okay, okay. Let's see. What solution are we getting from this? So you see, have you seen the solution now? And what do you get?
Almost that
Is this-
bad.
Found 2.59172.
Okay, so obviously this is
74.
approximation, just approximated for us, not so. Okay. This is a solution, of course. So there's just one note, of course, because if there were different routes, it's going to give us those different routes. There's just one note, of course. Okay. All right. So let's go back. Okay, let's go back to this. Okay.
I have a question
Yes,
before we
please.
go far. So like the way we found the answer, that's approximating, that's less than 0.05. When they say you leave it to 3 decimal places, which one do you leave? The one that's less than 0.05 or
Of course,
this
the
other
one
one where
that,
we're
yes,
solving?
the present value that we've actually found, this one,
Or
x2.
that's
So
the
that's the
one you
one.
leave. Okay.
Yeah, it's the one that you present as the answer.
Okay.
Yes, yes. Now, I heard you talking about decimal places. Which one are you referring to?
No, I'm referring to the one from bisection method,
Because
number 1.
you have to be very, very careful in this course when you're told that, okay, approximate your answer to whatever decimal places. They're not telling you that you have to round off these to 3 decimal places. I'm sure I explained this earlier in the other videos. What did you mean? Do you remember?
I think I'll just watch because I think I only remember the one for the significant figures.
So for decimal places, I said it's when you have 10, it's 10 to the power negative number of decimal places. That's the condition you have to check. For significant figure, I said is what? 5 times 10 to the power negative number of significant figures.
Oh.
Remember this?
Yes, yes.
Yes. So be careful when you say no decimal places, no Shan. Just be careful on that one. It's not actually the actual decimal place that you have known from grade 7. Okay. So let's look at the next question now. I think we are done with this one. Unless there's a question. Is there any other question somewhere?
Oh, yes.
Yes, please.
On the table,
Mm-hmm.
So where you started counting from 1, since our x naught was 2.4, can I add it to the table?
Oh, yeah, you can actually add it. It's fine. You can add it. So you can say, okay,
0, then 2.4.
so here to be now, yeah, you could apply from 0, n, so meaning the values of n is starting from 0. Okay, so if you you create another column here, this will be 0, and then here it means we are going to have 2.4, and then to start 1, you found 2.6, 2, you found this. It's okay.
Yeah, because
Yeah.
I forgot that we had 2.4.
All right. Yeah, it's just fine.
Okay.
Yeah.